Hi everyone, very good morning to all. Welcome to ECS very first Additive Manufacturing live webinar, Bridging the Gap of Traditional Processes. I'm Terry, Division Manager of ECS, and I'll be assisting to co-host in today's webinar. So just a few housekeeping notes to take note. At the bottom of the screen, you will see the Q&A tab. So please utilize the section to ask any questions. We will be answering the questions at the end of the webinar, and we will try to answer as many as we can. Any questions we are not able to get to, we will send to a specialist who will reach out to you directly. And today we will basically covering, focusing mainly in 4 segments. Omar, the slide, thank you. All right, we'll be basically focusing mainly in 4 segments. What is limiting all traditional manufacturing processes? Why is 3D printing already changing some of the most advanced industry? How 3D printing is growing and why your industry is next. An introductory to the tools in digital production. So we will close the webinar with the Q&A section. And for now, please allow me to take this opportunity to do a quick poll to understand you better. So allow me to start the poll. Yep, so as you scroll down, you will actually find 3 questions. Select the option that best fits you. It should take you about 15 seconds. So once you have completed, just click submit. Okay, can see some of you have completed. A few more to go. Okay. All right. Let's end it here. And okay, so this is the result. Which industry best describes you? There's about 33%, 8% from the aerospace, 70% from consumer, 8% from electronics. Which best describes your understanding of additive manufacturing? I would say the majority will be on the basic. How many printers do you or does your company owns? And I would say majority will be none, and 42% 2 and above. Okay, nice. All right, so to begin off, let me do a very brief introduction on the company profile. Okay. So ECS has actually started since 1982, and we have been providing a comprehensive range of world-class CAD/CAM CAE solutions to the manufacturing, aerospace, marine, and offshore industries, mold makers, and many others. So we started 3D printing business way back in 2008. And in 2017, we did a very drastic change. We restructured the whole business offering, focusing just on 3D printing. So as I'm speaking now, year 2020, after 12 years involvement in 3D printing, we have expanded our presence across ASEAN and started our office operation in Thailand and Indonesia, as you can see right here on the screen. So without further ado, together with me is Omar. He will be the presenter for today. He is an application engineer whom actually specializes in assisting customers across all industries to integrate additive manufacturing into the current workflow. Okay, over to you, Omar.
All right, okay. Thank you, Terry. Thanks so much for the introduction. And good morning, everyone. Hope you're doing well. So as Terry has mentioned, we will talk in this webinar about 3D printing and how it's changing the way we do things. So perhaps for us it's very good that we did the poll in the beginning, and we thought about starting from the basics, trying to understand what 3D printing is trying to understand how did it came about and what is, what makes it different from most of the traditional manufacturing processes and what makes it that people talk about it these days. It's good that majority I see might have like a basic understanding of the technology, and this is something very understandable. At the end of the day, this is the new technology. So perhaps for us to, or for me to better define what 3D printing is, we have to first understand how manufacturing or how mass manufacturing is being carried out and what processes are being used and what are the shortcomings that we see in this manufacturing industry that we can find a place for 3D printing to complement it and overcome those shortcomings. So if you were to talk about traditional processes, I just listed here 4 of the main ones that we see in many industries. So for metals, we do something such as casting, whereby you pour the liquid molten metal inside of a mold. For glasses and polymers, we mostly process them by molding, whereby you build those molds to create the shape. Then sometimes we have to do something such as this, deformation. So processes such as rolling, forging, drawing, or in this one like bending. And sometimes we also use powder, that's again used in metal. And this is important, and that's why I have it here, because we'll come back to that later, whereby you create the shape in powder and then you center that inside of a furnace. But this is just the primary processes that we do in most of the traditional manufacturing processes. Of course, there are many other processes, but those are the commonly used ones. So after that, we have a very famous one, which is machining. So in machining, you need to cut the part, you need to maybe drill it. So in case of, let's say, some of those smartphones that would have an aluminum casing, when you have the rough shape, you have to do machining. And then after that, you start to do something which is finishing. A bit of grinding, maybe plating, all of those steps are needed just for you to attain the aesthetic requirements of the part, of what the consumer product would look like, as well as that to attain the mechanical properties that would make this casing, let's say, functional. And of course, you may know that any mechanical components, they're being manufactured separately. And then you have to go on and join them all together in what's known as assembly, for instance. So roughly all manufacturing processes look something like this. If you're talking about plastics, metals, or ceramics, they have to be processed in such a way which is quite similar to what we just highlighted. And if you were to think about the visuals that I just shown, like casting process or molding, maybe bending over here, you would see that all traditional manufacturing processes, actually anything that we manufacture, have to utilize molds and tooling to create the geometry. There is no way you can go on and create the specified shape of a plastic without not having a mold. You have to have a mold. So some may ask, okay, so what are the issues with using mold and tooling? We've been using those for the bigger part of history. Any sort of manufacturing, even from the early civilization all the way up until now, has been utilizing and capitalizing on those molds and tooling. Of course, the mold and tooling manufacturing is also, it became much more advanced. So in the early days, milling machines used to be manually operated. The tolerances were not so great. And now we have the state-of-the-art CNC machines that can go into nano machining, that can give you very high precision with very tight tolerances. So precision-wise, traditional manufacturing has, expanded massively in this area, but there remains to be some constraints and drawbacks when it comes to molds and tooling. And those restraints actually, in turn, give you the same drawbacks for all traditional manufacturing processes. Firstly, we have design constraints. We have the problem of longer lead times. We have another issue that the tooling is quite expensive, and that leads to supply chain complexity. Now, in the next slides, I will go in depth a little bit more into what makes those issues, come about. So when it comes to design constraints, if you were to do any mechanical engineering course, you'd have to spend at least 2 years to wrap your head around the idea of design for manufacturing and assembly. So if you're a designer and you have the best design in the world, if this design of yours cannot be manifested into something that can be manufactured and assembled together, then your design is no good. And of course, those imposes this ability for you to do an assembly or to produce something that can be manufacturable imposes a lot of restraints on your design. So for instance, if you'd like to build a very complex shape, such as what I have here, like a topology optimized shape, there is no way you can do this with any traditional manufacturing processes, because at the end of the day, you're restrained. You cannot machine, or you cannot create a mold that would create such a complex shape. So this where design constraints come about. Now, there are issues with the costing. Mold and tooling are expensive. And the reason why they're expensive, perhaps we will talk now, we'll take a good example, which is injection molding, the process by which all the plastic parts that we see around us, from let's say remote controls to your glasses, are made with. So a typical mold for a very simple part like this one would have to be manufactured in those steps that I just have a representation for. So it's processed first in powder, it's being machined at a very higher level, and it's quite expensive. A simple mold like this one can cost you maybe $5,000, $6,000. So perhaps this graph is what you also see for many of the mass manufacturing processes when it comes to their pricing. You see this exponential decay. You see that if you're talking about low volume production, the pricing per piece is quite expensive, and it's only worthy of going into full-scale production for you to attain the good pricing or cheap pricing when you, in the case of this simple part, exceed the 5,000 part count. And this is what the composition cheap. This part can, let's say, based on what the information you can find, can cost you maybe around $6.40. And you see that the cost is predominantly that of the mold. It's only worthy for you to go into injection molding when you talk about 500,000 parts. Only then you see the drastic change, and you see the part price reduced to almost 40 cents. And when it comes to lead times, perhaps we have to talk about the development timeline of traditional manufacturing process. Again, we're choosing injection molding. So there are 5 main steps that you have to take. All processing of injection molding, you'd have to start with the part design. That maybe takes you 1 or 2 weeks, depending on how complex the part is. And then that's not all. You have to design the mold. This is a more complicated step for you to take. Then you start with the mold fabrication. And we've seen the steps. You start with powder, you start with machining. It's manual, labor-intensive process, and it's quite expensive. Then you start to do some trials, because in many cases, when you go into injection molding, the shape that you create is actually created by the tooling and not created by the part design. So the shape can be a little bit, there can be discrepancies between what comes out of the mold and what your customer has in mind. And this, again, opens the door for all what we know in terms of design, which is iterations or refining of the tool. So you need to undergo many iterations or do some adjustments. And in some cases, you have to maybe throw the mold that you've built and start building a new one that costs you maybe $5,000 again. So the whole thing, the whole timeline to develop and to run a project in injection molding, if let's say we're talking about a complex part, can take up to 22 weeks. And this is quite a lengthy time. And everybody knows that if you want to go into injection molding, this is the lead times that you're talking about. So we've seen, okay, this is some of the issues that comes about in traditional manufacturing. So what about a process which is known as 3D printing? This process that starts off in the very same step, such as any traditional manufacturing process, or in this case, let's say injection molding. So you need to do a part design. And from there, once you have a 3D model CAD file, you can directly print. And all you need to do after that is just some minor post-processing, which in plastics can take you maybe 1 to 2 hours. So just for me to give you the book definition of what 3D printing is. So 3D printing is known as additive manufacturing because it prints or it builds a part layer by layer in an additive process. And right now in 3D printing, we have the ability to use metals, plastics, ceramics. So most of the commonly used classes of materials that we have can be 3D printed. So perhaps we have to also talk about how did 3D printing come about? And the idea of 3D printing was first introduced, I guess, around the mid-80s by this guy here named Chuck Hull. And he used a thermoset, which is liquid resin, and cured it with light to be able to create the shape layer by layer. So how did it come about? And what actually inspired him to go on and do 3D printing in the first place? The industry at the time did not have a similar technology. And what inspired him was how hard it was for designers to go on and do any prototyping. So, you know, we've seen how hard it is. It takes you maybe up to 22 weeks to run an injection molding process. Imagine that you're a designer and all you need just to do is to come up with some different concept, you know, physical parts to do some verification before you go into production. It doesn't make any sense to go and run an injection molding program, for instance, to get some of those parts, because you see that that part will cost you maybe $5,000, $6,000, depending on the mold. So what designers used to do back then, and Chuck Hull used to be one of those designers, he used to work in a furniture company, is that he would need to go down and get the styrofoam and start machining it or using whatever, you know, subtractive techniques that he can do and add a bit of color so that he can manifest those concepts into an actual product. Now, the process was very lengthy, very tiring and hectic. And therefore, Chuck Hull told, okay, now we have 3D models. That was about the time that 3D models and the idea of CADing started to appear with the computers. So he thought about attaching or building this SLA printer, as you see in the picture, putting it next to his computer and start this additive manufacturing technology. So you can, I believe that you might have come across those terms before: rapid prototyping, 3D printing, additive manufacturing. It's all talking about the same technology. So when the technology, for the bigger part of its history, from its first introduction by Chuck Hull all the way up until, I guess, maybe 2012, 2013, used to be known as rapid prototyping because it emerged for prototyping, and it was not intended to go into additive manufacturing or to go into any manufacturing process. But what made this technology actually evolve, we will talk about this later on, and we will see why it's now a standalone type of manufacturing. So 3D printing has come a long way since the 1980s. So we now have probably like 7 main different technologies. Some are using powder, some are using resin, some are using solid. I'm not going to be talking in depth about what's the difference between those technologies. We have something such as material jetting or powder bed fusion. We will keep that for a future webinar because every single technology of those complements 3D printing in a way and has its uses in applications. So for this one, I will just focus more on the toolless digital production, which is coming up next. And this one uses actually resin printing. So the whole suite of technologies that we see in 3D printing was able to transform the technology and take it from a place where parts used to look like this, not a very nice looking parts, cannot go into much, you know, engineering related fields, to parts that are functional, to parts that can go into very advanced solutions. You see here something such as those microfluidic chips that goes into the medical industries, or textured parts that looks like injection molding. So the technology has come a long way in the past 30 years or so. So, and this is also represented by how we see the total revenue of this industry growing. 2018, it was reported that it had a revenue of around $10 billion, and it's now projected to go up to $35 billion by 2024. So in just 6 years, you're talking about more than 300% of increment. That's a massive number. And I wouldn't say that the technology is by any place mature when it comes to its adoption in different industries, but we're starting to see better trends in those advanced manufacturing technologies such as aerospace, in medical. We can also see good adoption here in the automotive. It's not uncommon from us, and this is quite recent, from January 2020, that Boeing or GE is, by the way, also one of the big players now in the 3D printing realm. that they have 300 3D printed parts inside of their latest engine, the GE9X that goes into the 777X. So what makes 3D printing lucrative and attractive for those advanced manufacturing technologies? And perhaps the way I see it, actually, what makes it quite important for them is that they can finally break out and they can finally remove the restrictions from the design for manufacturing and assembly that we talked about, and utilize something as what is known nowadays as design for additive manufacturing. And it's the ability for you to design the part, for its specific purpose. So if we were to talk about parts or things are being manufactured, let's take this as an example. You can find this as a bracket, and it can be done by normal machining. So it's used to connect some rods maybe together, but you end up having to have this mass of material that doesn't serve any purpose. So the reason why you have it is because it's extremely hard for you to machine such a shape or to create a mold for such a complex shape. And then in industries such as aerospace, where every kilogram is corresponding to $3,000 in terms of fuel consumption every year. So imagine how many kilograms that you can save by transforming your design from something such as this to a light structure that is just supposed to do its function. So the same trend is being now used in automotives and motorcycles. It's again using this topology optimized structures that mimics what is known as how nature builds in a way. So nature builds differently than how we build in traditional manufacturing. If you were to think of trees or our bones, for instance, they are extremely light. They're hollow from the inside, yet they are quite strong. So the ability for you to go and print those structures, only 3D printing or additive manufacturing is a technology that can be used to attain such a complex structures. And we see this in medical implants, whereby the parts or the bones that you build mimics what we have inside of our bones and have maybe lesser rejection rates for patients. And that's why generally we see aerospace, medical, automotive starting to utilize 3D printing. So what about plastic parts? So it's true, the technology actually emerged in plastic manufacturing. The very first technology that we had was SLA, the one that uses a laser to cure liquid resin. But in my opinion, I don't think that the technology had much of an impact when it comes to the production of parts. So it's always been stuck in this step of prototyping. And then when it comes to production, then people don't go around and use 3D printing. But this trend has finally changed very recently. So now we have something known as the toolless digital production. And that's the main trend or the main newer thing that I just want to talk about today. And it's the ability for you to stack up parts, build maybe hundreds in a very few number of hours. So this video would be a very good representation to what the technology is able to do. So you see here, again, it's using liquid resin, and the parts are being pulled outside of that resin at a very high speed. So all of those parts are actually injection molded like parts when it comes to their properties. And the reason why we're still using resin on the Figure 4 platform or the non-contact membrane technology is that the resin, compared to, let's say, powder bed based systems, allows you to have the looks and feel of injection molding. So you can have smooth finished parts. And we can also see that the manufacturing solution comes along with a scalable options. So you can have up to 24 building chambers all running at the same time. So imagine if, let's say, you have just 10 building chambers and you can print up to 1,200 parts, functional parts, in 5 hours. That's astonishing. And you may ask me, okay, so was it just speed that was limiting this resin technology from the start to go into production? I mean, we've had it for 30 years. You could say, okay, I can, sometimes you need to roll out a product in limited edition. You might just need to have 50 or 100 parts. So why were not people using resin back then? And the reason for that is that the fundamentals of how any resin printing technology works is pretty simple. You get a liquid resin, you cure it with light, and there you have it. You have your physical part. So the chemical reactions look something like this. The chemical compound of the resin would have those monomers, oligomers, and then the whole reaction is initiated by UV light to create those interlinks between the photoresin that allows the part to solidify. So this perhaps is a good analogy. Same as maybe the sun and our skin. A little bit of sun is good, okay, allows us to grow, gives us maybe vitamins, but an extended exposure to sun is not good. Same thing for parts that are built with resin. So perhaps if you're experienced with 3D printing and you've printed a white part before, you tend to see that the part tends to go and decolorize, turns a little bit yellowish after some time, after maybe a few months. And the reason for that is that the extended exposure to UV actually degrades or weaken those links, and the part mechanical properties start to degrade. So the part is not really very much reusable. But 3D printing now has evolved, and newer resins have been developed for this non-contact membrane technology. And those resins, you can see here, this is a good test whereby an aging process was done for what we see on an elongation to break or tensile testing for 2 years, 5 years, 8 years mark. And you can see that the properties of those parts are holding up for up to 8 years of aging. So you no longer need to, like those parts are very similar to injection molding. They can go into most of the end-use application. And perhaps one of the good things about using this toolless digital platform is that the same printer can allow you to do concept and drafting, which is, think of it as the very early stage type of prototyping, just for you to build the part, visualize it. Then you can also take it to the next step. You can now have parts that mimics what you get on injection molding. So if you need to do some functional testing, snap fits, some assembly, then you can do that with this technology. Then it goes all the way to do directly production parts, same as what we've seen in the video. So those parts are certified and can go into end-use applications. And it can even go into some of the more stringent requirement kind of industries, such as medical industries. And the reason why you can go now into medical industries, if you're talking about medical, then you have to sterilize the parts at, maybe 100 degrees Celsius or above. So before that, like most of the resins that were developed all the way up until maybe 1 year back, didn't have the ability to withstand such an elevated temperatures. But now it's also possible for you to do so with this new resins that were developed. And you can also use it to do some casting patterns, maybe for silicons or for metal. So you can see here the flexibility that comes about with using this 3D printing technology. Some materials, again, have this excellent UV stability. They can go into humid conditions. They are ISO standard certified. They can go into thermal applications. So they're very similar to what you get on injection molding. So, okay, a good question now for us to ask is, comparing this to injection molding, what does the numbers look like when it comes to a direct comparison between the toolless digital production and injection molding? So 3D Systems have ran this survey. They chose one part, which is like an AC vent for a car, and they gave this part to some of the people who do injection molding, like contract manufacturers, and they came up with this kind of figure. So you see here, when it comes to tooling design, you no longer need to do that in 3D printing. So no time is being spent, and the labor cost for you to do and build the mold, let's say on a traditional injection molding, is around maybe $4,000, and compare that to just maybe $121. This was the money that was spent for a designer just to prepare the file and so on. So for as quickly as 92 minutes, you can have your hands on the very first part that can go into the end use application. Compare that, and this is quite a simple part. So they said, okay, in a matter of 15 days, we can get our hands on a part by injection molding. And you can see here that for 500 parts, the pricing per piece is actually cheaper than injection molding. it's only worthy for you to go into injection molding if you're talking about maybe 10,000 parts, whereby the pricing of injection molding would be like $1.30, compare that to the same pricing. So that, again, 3D printing, when it comes to pricing, it's the same regardless of what the quantity is. But again, you have the ability to adjust this design, customize it, and do all sorts of different textures that can be applied at no additional cost for virtually all parts that you printed. So the key advantages, just for me to summarize it, is lower costs. So of course, you no longer need to build tooling. You no longer need to employ someone to build it and spend the time and resources and money. So overall, it's lowering costs. It allows you to tap on the complexity of the DFAM, the design for additive manufacturing, that we've seen in aerospace and in biomedical industries. Same as those industries, you can now have the flexibility and you can design unmanufacturable parts. It allows you to do more customization for your customers. And this one is very important, the elimination of physical storage. So we've seen that the supply chain of any traditional manufacturing process is quite complex. And the reason why it's complex, because traditional manufacturing is very worthy for you to go if you're talking about hundreds of thousands of parts. And when you produce hundreds of thousands of parts, you need to store them physically in a warehouse. But when you can print on demand, then you no longer need to store any of those parts and you just print them on demand. Now, one of the other key advantages of using 3D printing in production is that many parts, especially those aerospace parts, they can be an assembly of 20 parts all reduced to one single part that was directly printed. So we've seen in the very early slides how we always have to have this joining process, this assembly process, because mechanical parts come along as a system, and all parts have to be assembled all together. But in 3D printing, you can actually eliminate this step altogether and simplify the process. And perhaps I believe this is also another important thing to highlight, is that this technology, not just, it can be placed or it can be positioned as a standalone kind of manufacturing technology, but it also complements the existing production methods. So, okay, you can come to me and say, I'm a contract manufacturer. I only deal and I only produce parts in, let's say, for a customer, I'm talking about 1 million parts, and I'm not interested in winning over the low volume quantity of, let's say, 500 or 1,000 parts. Because think about it, like a very simple math, we've seen, like when you exceed, like for the simple cover part, when you exceed the 500,000 mark, you're talking about 40 cents per one part. So if you were to sell a million part and you cap it at $1, that's about $1 million worth of revenue. That's a big money for contract manufacturers. The thing is about these days is that you're no longer just competing with your local rivals. You're talking about, we're living in a globalized world that virtually your customers can go overseas to China, to Philippines, to Vietnam, to whatever the country may be, and have the same project ran over there and maybe half the price. So the only way you can win deals is by you reacting fast. That's very important. So I will conclude this presentation by just showing one case study that we just ran with a customer here in Singapore, and this is a medical company, and it was also related to COVID-19, where they were engaged by one of their customers and asked to go on and start producing thousands of parts. But of course, in the beginning stage, they need to come up, like our contract manufacturer has to develop the design. So they came up with 6 different designs in this case, and they needed to deliver those functional parts as quickly as possible, test them on patients, so that if they develop the correct design, their customer is happy, only then they would sign the deal to go into production of producing 1,000 parts per day. So that's a very high volume production that the Figure 4 or the non-contact membrane technology cannot really attain to. So what we've done with them is that, on the same day we printed the part. It took us around 2.5 hours, 30 minutes of post-processing. Parts were delivered in hand to them 3 hours later. And on the following day, they did trial runs with those parts that you see here. Those were printed with the Pro-Black material, it's a biocompatible material, and tested on patients. And on the same day, once the design is verified, everything is good, they managed to close this deal and win over the production one. So this I believe gives you a bit of understanding of how 3D printing came about, where do we see it in the industry, where parts, it complements some of the traditional manufacturing processes. We also have a plan to run more webinars in the future where we were to go more in depth into case studies and some of the practical uses of 3D printing, talking about some of those, technologies that I just highlighted and how it's being used in different applications. So with that, I believe that will conclude my presentation for today, and we are open for the Q&A. So thank you so much.
Okay, thank you, Omar. Thank you for your presentation. Well, I'm going to go ahead with the Q&A. So if you have any questions, please key in at the Q&A tab below your screen. Right, and okay, we got our first question in.
All right.
Right, and this question is, you have shown some parts with different textures. Are those printed straight out from the printers, or do you require any other post-processing to achieve that?
All right, okay. So as I mentioned, the advantage of using resin remains in the surface quality. So powder bed-based systems such as SLS or MGF, unfortunately, does not give you that smooth surface finishing. And the resin printing can go for as low as sometimes even 1 micron layer thickness so that you can attain those kind of textures. So those textures in 3D printing, you can just have the 3D model of yours, the part that you designed, and you go maybe into ZBrush, and we already did that multiple times in ECS for some customers. You go into ZBrush if you have some designer or Rhino, and you create whatever kind of texture that you need. And once you apply this to your 3D model, you can just directly print it. So you don't need to do any additional processes to attain those surface finishing. No, it doesn't come at any additional cost, and it's directly printed.
Okay, awesome. All right, and our next question is, how can 3D printing help in smart manufacturing?
Oh, okay, that's a good one. So, okay, the idea of smart manufacturing, it's still in the early stages, but it's more related to IoT. It's more related to real-time feedback on data. It's about using, like robotic arms and running an autonomous factory that you can control. And 3D printing is a fundamental part, like in this smart manufacturing, because it allows you to print, without needing, like a laborer or someone to do machining. So it's mostly like hands-free process. I believe if a good thing for me to go into that slide, just a second. So this one is like, yeah, it shows, this is what I would think a good manifestation of smart manufacturing in the future. So the figure 4 production here is like, it uses robotic arms. It uses one control unit that you can control all the different building chambers. It's a hands-free kind of post-processing. It has its allocated post-processing here chamber at the end. So the whole production you can run, and it's completely hands-free. So you see the newer trends of this smart manufacturing all represented in the recent trends in traditional, in figure 4 technology. So yeah.
Okay, right. Okay, one more question here is, can you elaborate more on indirect production? What do you mean by indirect production, and which printer will be able to do so, in your opinion?
Oh, okay. So indirect production is, as you've seen, sometimes you might also print like the mold, or in many cases, we see this quite often in jewelry and dental applications, whereby you can create a casting pattern in like casting resin, and you use this to do casting. So again, it's the same thing as comparing traditional manufacturing to injection to 3D printing. You can have the part printed very quickly. You no longer need to do any tooling or any rubber molds. So I will talk more hopefully about this in the future when it comes to how we use the different technologies to go into indirect production. Worthy of noting, if you've came across those Invisalign or dental aligners, invisible ones, those are made by a process called thermal forming. So it's an indirect production using 3D printing. So there are many cases that, yeah, that can be done. And the figure 4 allows you to do sacrificial molds, printing patterns, printing, casting patterns, all can be done on this platform.
Okay, and one more question over here. How do you determine when to opt for 3D printing instead of traditional manufacturing? Are there any cost modeling that we can refer to?
Yeah. So the good thing about 3D printing generally is that the costing is very easy for us to process. So based on the part geometry, you would get the volume of the part, and from there, very easily on an Excel sheet, you can just straight away get the pricing of one part. So you compare this against traditional manufacturing for the volume that you're talking about. So let's say, as we've seen in this like case study, the part can cost you, let's say, $7.90 on 3D printing. Will it cost whatever kind of cost that you get on traditional manufacturing process? So you can attain the pricing, let's say, from your contract manufacturer, and from there you can also get a pricing from us, and you get to compare. So it's a pretty simple process.
Okay, and I think we got only time for one last question.
Okay.
Injection molded parts have high precision. Can parts that are 3D printed achieve that as well?
So, okay, let's talk generally. All right. So 3D printing in general different technologies comes with different accuracies and different considerations with their design. So resin, now using this oxygen layer or using continuous printing, allows you to pull the part continuously from the liquid resin in like an upward movement. So the accuracy of this technology is like 6 Sigma certified, and it gives you tolerances maybe 50 microns, 100 microns, similar to what you get on injection molding. But again, there's a catch. It's always better for you to attain or to adjust the design a little bit to make it better suited for 3D printing. So sometimes if you have like parts printed in resin that are with very thick cross section, because the part is quite heavy and is being built in resin, you can have some discrepancies. But I would say that mostly for plastic parts, such tolerances for small parts are quite attainable now with 3D printing as well. And we see trends in the industry whereby, especially for those automobile industry, car manufacturers such as Ford or Lamborghini, or for their special edition cars, they're using plastic parts in their dashboard that are customized, and they're all 3D printed with similar technologies, such as the one that I talked about, the toolless one. So yeah, it can definitely go into end use with no issues when it comes to, or no constraints when it comes to the accuracy.
Okay, and I believe, yep, that's about all. We thank everyone for joining us today. We hope the talk today will be of a value to you. And of course, if you ask any questions and we are not able to answer, do not worry about it. We will actually reach out to you directly shortly. So thank you again, and stay safe, stay healthy. Thank you.
Thank you.